Bismillahirrahmanirrahim. My name is Dr. Safir Abbas and I am going to teach this course which we called as Plain and Reinforced Concrete 1. Sometimes we also called as PRC 1. The code for that course is CE314 and this course is going to be taught by myself and Professor Dr. Asadullah Qazi. So some part of the course I am going to cover that and some part of the course is going to be covered by Professor Dr. Asadullah Qazi. The name of that course is Plain and Reinforced Concrete. So whenever we say reinforced concrete, meaning to that we have actually reinforcement in it and reinforcement in the form of conventional rebars. So conventional rebars are normally made up of steel. So we have concrete with steel reinforcement in it, we call as reinforced concrete. And if we say plain concrete, meaning to that we do not have any reinforcement or we do not have any steel in it. So in that course, we will study plain concrete as well as reinforced concrete. So in plain concrete, we will see the material properties of concrete, we will see hydration of cement, we will see properties of concrete in fresh state and hardened state, we will see how the curing of concrete can be taken place, we will study different tests that needs to be performed on concrete in order to check the quality of the concrete, then crushing strength of concrete, modulus of elasticity of concrete, and some durability properties which include alkali aggregate reaction, carbonation, and sulfate attack. Then we study adhesive or admixture of concrete, and we will also some part of cracks in concrete. These topics we will cover under the heading of plain concrete. Now in case of reinforced concrete, we will see the basic action of steel and concrete, stress strain curve for steel and concrete, actual and simplified stress block. We will see behavior of reinforced concrete member including columns, beams, slab at working and ultimate load. We will see which specification or code we will follow in order to design the structural member, and then we will cover simply supported rectangular and T-beam. We will cover one-way slab and two-way slab, and some part of column we will also cover in that particular course. Then we also cover shear and diagonal tension in concrete, design and detailing of flexural member of shear. We will see how we can provide reinforcement in case of corner slab, and afterwards in the lab part we will cover the physical testing for the concrete material, acceptance test for the cement, some fresh and hardened properties. We will test them actually in the lab. We will cast various beams. Textbook. Actually, we will follow two books. One is Design of Concrete Structure by Arthur Nilsson. Secondly, we will follow Concrete Structures Part 1 by Zaid Ahmed Siddiqui. These two are basically our textbook, and references book are Design of Reinforced Concrete by Jack McCormick, Reinforced Concrete by Edward Noy, and we will actually follow SCI code for the designing of the structural member. Now let's discuss regarding the evaluation of that PRC1 course. So as usual, mid-semester examination will be of 30 marks, end semester examination will be of 40 marks, class participation and assignment will be 10 marks, and there will be 2 quizzes each of 10 marks. So total evaluation will be out of 100 marks. Concrete. Concrete is actually a mixture of binder material, fine aggregate and coarse aggregate. Binder material, most likely it is cement, fine aggregate is sand, and coarse aggregate is crush. There is a limit between fine and coarse aggregate. If our particle size is less than 5 millimeter or 4.7 millimeter, we can say that it is fine aggregate, and if our particle size is more than 5 millimeter or 4.75 millimeter, that we called as coarse aggregate. Now, as I said, we have two different types of concrete. One we called as PCC and second we called as RCC. Plain cement concrete. Without reinforcement, we called as plain cement concrete. Plain cement concrete is weak in tension and strong in compression. However, in case of RCC, we include reinforcement actually. So it is a mixture of reinforcement, sand and coarse aggregate. Mixed proportional. Normally we write mixed proportion 1:1.5 ratio 3. This one, first one, meaning to that this is the cement ratio. 1.5, this is basically representing the sand, and this 3 is normally representing the crush. So if I say 1:4, meaning to that one part of cement mixed with 2 part of sand and mixed with 4 part of crush. Similarly, if I say 1:4:8, meaning to that one part of cement mixed with 4 part of sand and mixed with 8 part of crush. So let's say I use cement equals to 50 kg. So if I am using 1:4, so 50 kg is cement. If I multiply 2 part of sand, we will get 100 kg of sand, and if I use 4 part of crush, then 4 multiplied by 50, we will get 200 kg of crush. If we are using water cement ratio equals to 0.5, so we can get water divided by cement equals to 0.5, and if we are using cement equals to 50 kg, if we just multiply 50 with 0.5, we will get water equals to 25 kg. This is batching by weight. Either we can do batching by weight or by volume. For normal strength concrete, the water to cement ratio normally we use 0.5 to 0.6. In this slide, we will see what are the structural elements of a building and how basically load is going to transfer from structure of the building to the footing and ultimately to the soil. So we have basically that slab, which is basically in between this column and this column. This one basically we call as slab. This one we call as column, and these horizontal member, this one we call as beam. So first of all, this slab load is basically going to transfer to these beams, and from these beams it is going to transfer to the column. Again we have slab, first floor slab. This first floor slab load is going onto the beams, and from the beams it is going to the column, and from column it is going to be the column foundation, and from foundation it is ultimately transferred to the soil or the ground itself. Slab is actually a horizontal plate element which is usually designed to resist the gravity load. Beam is actually a long horizontal or inclined member with limited width and depth. Its function is to support the slab load. It is designed to resist shear force, bending moment and torques if any. Column is basically a vertical member which supports beams or slab load. It is normally designed for axial load and moment if any. Wall is actually a vertical plate element that resists gravity as well as lateral load. In case of a retaining wall, it is usually designed to resist shear forces and bending moment. Then we have stair. Stair is a structural member that provides means of movement from one floor to another in a structure. It is designed to resist shear force and bending moment. Then we have definition for foundation. Foundation is a member that support columns or wall loads and transmit them directly to the soil. The footing is designed to resist shear force and bending moment. Now load transfer mechanism. Load actually transferred from top to bottom. So first of all, from roof surface to roof slab, then on beams, then on columns, then on foundation, and then it is basically transferred to the subsoil underneath the foundation. Now merits of concrete structure. Actually, in case of concrete structure, we have a good control on the cross-sectional dimension. We can design any cross-sectional dimension and shape. Then, as we know that concrete is made up of cement, sand and crush, therefore it is easily available in the market. Sometimes if we compare with structural steel or steel structures, concrete structure are economical structures. Then concrete structure basically provide good insulation of noise and heat and does not allow them to transmit completely. Another merit of concrete structure is actually a good bonding between steel and concrete structure. Then we have a stable structure. As we know that concrete is strong in compression and steel is actually strong in tension. So combined together they give a very stable structure. Then if we compare with the steel structure, concrete structure has less chances of buckling. Similarly, aesthetically concrete structure give us good aesthetic as we can provide any shape in concrete structure. However, in case of steel structure, we are restricted with the shape. But in case of concrete structure, we can provide shape of our own choice. In case of concrete structure, we have lesser chances of rusting. Now, some demerits of concrete structure. The first demerit of concrete structure is concrete is weak in tension. Then we have increased self-weight, and if we compare with steel structure, concrete structure can have cracks actually. In case of concrete structure, the demerit is that we have unpredictable behavior. We have inelastic behavior, then issue of creep and shrinkage, and then we have limited industrial behavior. Most of the time, concrete is actually cast in situ. So we have limited industrial behavior, as in case of industry, we need to build actually using steel structure. So we do not rely on concrete structure if we want to get a faster construction. Now specification and code. Most of the time we will follow ACI code 31805. We have 14th version and 19th version of the code as well. So most of the time we will follow ACI code. Then maybe sometime we will follow H2 specification, and we will use ASTM standard for testing and American standard for testing and material for the testing of material. So most of the time we will use ACI code. Regarding code and specification, it should be noted that no code or design specification can be constructed as a substitute for sound engineering judgment in the design of concrete structure. In this structural practice, special circumstances are frequently encountered where code provisions can only serve as a guide. An engineer must rely upon a firm understanding of the basic principle of structural mechanics applied to reinforced or pre-stressed concrete and intimate knowledge of nature of materials. So basically code or ACI specification, they act as a guideline, but it will never be act as a substitute for sound engineering judgment. So design load, actually we have two different type of load. One we called as dead load, the load which do not change their magnitude and position with respect to time within the life of the structure. That we called as dead load. Dead load are actually two different type of. One we called as self load, which is the member own weight, and second we called as superimposed load. Superimposed load are those load supported by a structural member. For instance, self weight of column is self load and load of beam and slab over it is actually a superimposed load. Live load are those load actually with changing their magnitude and position with respect to time over the lifespan of the structure. They may be either fully or partially in place or not present at all and may also change in location. Their magnitude and distribution at any given time are uncertain. So live load are basically those load which is basically changing from time to time and changing its position. Now some important densities of material. So if we are using PCC, normally the density we need to assume is 2300 kg per meter cube. If we have RCC member, the density we need to assume is 2400 kg per meter cube. If we are using brick masonry, we need to use 1900 to 1930, any value in between those. And if we are using earth, sand or brick pellets, density for those is in between 1600 to 1800 kg per meter cube. Now intensities of live load. If the live load is not given, then for residential, house or classroom, we can assume 200 kg per meter square. If we are designing office building, the intensity of live load we can consider 250 to 425 kg per meter square. If we have a library reading room, we can assume 300 kg per meter square. If we have a library stack room, we can consider 730 kg per meter square. So this is the table basically if we want to use the intensities of the live load. The basic design equation is applied action multiply with factor of safety that needs to be equals to maximum internal resistance of the member. Now factor of safety is equals to maximum failure load divided by maximum service load. Now why we provide factor of safety? In order to cover uncertainties due to applied load, due to material strength, uncertainty due to poor workmanship, uncertainty due to unexpected behavior of structure, due to thermal stresses, due to fabrication processes or due to residual stresses. Also, factor of safety is provided in order to cover the natural disasters. Now design method. Actually we have two different design methods. One we call as ultimate strength design method or LRFD method, and second method is allowable strength design method or AST method. In case of LRFD method or strength design method is based on the philosophy of dividing the factor of safety in such a way that bigger part of factor of safety is applied on the load and smaller part is actually applied on the material strength. So material strength is greater than or equals to applied load multiplied by factor of safety 1 multiplied by factor of safety 2. So smaller part, we have two factor of safety. The smaller part needs to be applied on material strength and bigger part needs to be applied on load actually. So FS1, which is FOS1, factor of safety first part, it is actually greater than 1. This is bigger part and that needs to be applied on the load and normally we call it as load factor. Now this part 1 over FOS2, this is smaller part and we call it as strength reduction factor, that needs to be applied on the material strength actually. This is the philosophy of ultimate strength design method. So phi Sn needs to be greater than that capital U. So phi is again strength reduction, Sn is nominal strength and this combined together phi Sn. This is design strength and that capital U is actually required strength. So for members subjected to moment, shear and axial load, phi Mn needs to be greater than Mu. Phi Vn needs to be greater than or equals to Vu. Phi Pn needs to be greater than or equals to Pu. So this M is basically moment, V is shear and P is axial load. The second method of design we called as AST method or allowable stress design method. In case of AST method, the whole factor of safety is actually applied on the material strength and service load are taken as it is, meaning to that no factor is going to be applied on the load. So material strength divided by factor of safety, that needs to be greater than service load. In both allowable and ultimate strength design analysis is going to be carried out in the elastic range. Now other type of design we called as plastic design. In case of plastic design, plastic analysis is carried out in order to find the behavior of structure near collapse state. In this type of design, material strength is taken from the inelastic range. It is observed that whether the failure is sudden or ductile. Ductile failure is most favorable because it gives warning before the complete collapse or failure of the structure. Now we have two things. One we call as analysis and second we call as design. In case of analysis or capacity analysis, we have given size, we know the shape, we know material strength, and we know the cross-section dimension. We are interested to find out maximum load carrying capacity of the structure. That we call as analysis of a structure. If we want to find out maximum load carrying capacity, that we call as analysis of a structure. If we have given load, span and material strength and we want to find out cross-sectional dimension and reinforcement in it, that we call as design of a structure. So I am going to repeat again as this is important. In case of a design, we want to know the cross-sectional dimension and reinforcement in it. However, in case of analysis, we want to find out the maximum load carrying capacity of the structure. Actually, there are two objectives for the design. Structure needs to be safe first and then structure need to be economical. So safety and economy, these are actually two important parameters. But first, structure need to be safe and structure needs to be economical. Now we have load combination. Most of the time we will use that load combination 1.2 times dead load plus 1.6 times live load. Other load combination are 1.4 times dead load, 1.2 times dead load plus 1.6 live plus 0.5 times LR. LR is basically live load on the roof, but most of the time we will use this load combination 1.2 times dead plus 1.6 times live load. Now strength reduction factor or phi factor, if we have member needs to be designed in bending or flexure, we will use phi equals to 0.9. If we have compression control member, column with ties, we will use 0.65. Column with spiral, we will use 0.75. Shear and torsion phi factor, we will use 0.75. I will explain later on what are ties and what are spirals. Shrinkage is actually a reduction in volume of concrete due to loss of water. Loss of water may be due to evaporation, or loss of water may be basically due to consumption during the hydration process. Coefficient of shrinkage actually varies with the time. So it is 0.00025 normally at 28 days, it is 0.00035 at 3 months, and it is 0.0005 at 12 months. So shrinkage is actually equals to shrinkage coefficient multiplied by length. Excessive shrinkage can be avoided by proper curing during the first 28 days because half of the total shrinkage take place during the first 28 days. Now creep is actually slow deformation of a material over considerable length of time at constant load or stress. Actually creep is a function of compressive strength. So specific creep at basically for 20 megapascal compressive strength is equals to 145 10 to raise power negative 6 per megapascal. Now for 30 megapascal concrete strength, specific creep is 116 into 10 to raise power negative 6 per megapascal, and so on. Now what is compressive strength or specified compressive strength? Normally it is denoted by FC dash. Whenever we say compressive strength, it means that we are talking about 28 days slender strength of concrete. If the slender has dimension 150 mm in diameter and 300 mm its length, and we find the compression strength at 28 days, that particular value we call as compressive strength of concrete. So whenever we say compressive strength of concrete, it means that compressive strength at 28 days. According to ASTM standard, at least 2 cylinders needs to be tested and their average needs to be taken. According to ACI code, for concrete design and constructed in accordance with ACI code, compressive strength should not be less than 17 megapascal or 2500 pounds per square inch. Now according to BS standard, compressive strength needs to be figured out on a standard size of cube 6 into 6 into 6 inch. So ASTM say compressive strength on slender specimen, and British standard says compressive strength on cube of size 6 inch. British standard recommend testing of at least 3 cubes and taking their average as the compressive strength of concrete. Now again, compressive strength is basically strength at 28 days. Normally slender strength is 0.75 to 8 times the cube strength. So slender strength is 0.75 to 8 times of the cube strength. This slide just shows the slender testing. This is the slender, and this slide shows the this picture shows the cube testing, concrete cube testing. So this is the cube, 6 inch, 6 inch, and other dimension is 6 inch, and this is actually cylinder. So cylinder is in accordance with STM standard, and concrete cube is in accordance with British standard. Now mixed design for concrete. Normally the ingredient of the concrete are mixed together in order to get a specified required strength. To avoid understrength of concrete, this required strength is set as a target strength. Normally that FCR dash, which is basically required strength or target strength, needs to be greater than the compressive strength. Now at the initial stage, how to get the targeted strength or required strength? If we have previous data available and if our compressive strength is less than 35, then our required compressive strength is compressive strength plus 1.34 SS. SS is standard deviation of compressive strength data. And if we have FC dash greater than 35 megapascal, then we have required compressive strength is equals to compressive strength plus 1.34 SS, and SS is compressive strength test. Standard deviation of compressive strength test. Now let's say if we do not have previous data to establish this sample standard deviation, then we have, if compressive strength is less than 21 megapascal, the targeted or design compressive strength is equals to compressive strength plus 7 megapascal. If we have compressive strength is in between 21 to 35 megapascal, then required or targeted compressive strength is equals to FC dash plus 8.5. And if our compressive strength is greater than 35, then required or targeted compressive strength needs to be equals to 1.1 times FC dash plus 5. Now the stress strain curve for the concrete. The typical stress strain curve for the concrete is something like that. The initial 40% of the maximum value of stress strain curve for concrete we will consider as linear elastic portion. From here to here, that crushing strain, normally we assume crushing strain for the concrete equals to 0.003. So two things are important from that stress strain curve. One, the initial 40% we assume as linear elastic portion, and secondly the maximum crushing strain for concrete we assume 0.003. Now the modulus of elasticity E value for the concrete, we have three different actually modulus of elasticity for concrete. One we call as initial tangent modulus, which is basically the tangent of the initial straight line. Then we have secant modulus, which is actually a line from 0 to the point where we are achieving 40% of the FC dash. And third, we have tangent modulus, this one. Normally for design purposes, we use secant modulus, which is basically at 40% of FC dash. ACI has given an equation for secant modulus, which is EC, which is secant modulus for concrete is equals to 0.043 WC under root FC dash. WC is actually density of concrete in kg per meter cube. FC dash is specified slender strength of concrete. If we assume for normal weight concrete the density equals to 2300 kg per meter cube, EC modulus of elasticity for concrete, we will get 4700 into under root FC dash. Now reinforcing steel, actually we have two different type of steel. One we called as plain and secondly we call as deformed bar. Now we only use Deform bar. Deform bar are those which have longitudinal and transverse ribs, or sometimes we called as lugs. Ribs provide actually a good bond between steel and concrete. The important properties of steel reinforcement is Young modulus, yield strength, ultimate strength, size, and actually diameter of the bar. This is the typical stress strain curve for the steel. We know that this is yielding, this is the ultimate point, this is the rupture point. In design, normally we use up till the yielding. As we said, in both AST and LRFD method, we will use elastic properties. So we have three different grades. Grade 300, Fy is 300 megapascal. We have grade 420, we have 420 megapascal, and we have a grade 520. These are typical stress strain curve for these respective grades. As I said earlier, in case of steel rebar, actually we use bilinear curve. So this stress strain curve. So up till yielding, actually we consider. So this is lecture number 1. This is a basic general introduction of the concrete or PRC1. I would suggest you must need to read the book. This is actually chapter number 1 from Zaid Ahmed Siddiqui book. You can get that book actually from Strength of Material Lab. So I would suggest you need to be read chapter number 1 of Sir Zahid book. Thanks.